So we're going to practice our new process of finding a polynomial function to approximate another function by making all the derivatives match. We're actually going to find a function for a polynomial for a function we found in the last section, and we'll see how closely they match using our transforming of 1 over 1 minus x in the last section to going through and finding a way to make the 0, the first, the second, the third, etc. derivatives match. Okay, if our goal is to make a 4th degree polynomial, so a polynomial that has x to the 4th in it, and we want the function value and then the first, second, third, and fourth derivatives to match, I'm going to have to actually go through and find the first derivative, for example. So, we'll start with the actual function value. If I want my actual function value to match, I need to know f of 0, and I'm going to need to notice that if I plug in 0 to my polynomial, all the rest of those terms cancel out. So f of 0 should equal a0, which in this case f of 0 is just 0. So I've chosen a sub 0 is going to equal 0. Now I'm going to try to make the first derivative match. So I'm going to need to figure out the first derivative of the function natural log of 1 plus x. I'm going to need to figure out what the value of the derivative is when x equals 0. I'm going to take the derivative of my polynomial, and I find out that in order to make my polynomial function have the same first derivative at 0 as the function I'm approximating, I'm going to need a1 to equal 1. I'm going to keep going through this process. So now I'm going to need the second derivative. I'm going to need to evaluate the second derivative at x equals 0. I'm going to need to take the second derivative of my polynomial. Don't worry, there's a shortcut. And then I'm going to need to figure out what I should let a2 be so that my second derivative will be correct. So here's my second derivative, negative 1 over 1 plus x all squared. So the second derivative evaluated at 0 should be negative 1. Whoops. Which means when I find p double prime, it tells me that 2a sub 2 is going to equal p double prime of 0. And I can figure out that a sub 2 is going to equal negative 1/2. Oh, that's interesting. Because in the first problem I did, my a2 also had a denominator of 0. So we're going to see how that helps us. All right, so you can see as I continue through this process, I'm going to be able to figure out a3. Interesting, I have a denominator of 6 in my a3. And when I figure out a4, interesting, I have again a denominator of 24 in my coefficient of the x to the 4th term. So let's collect together this polynomial now that we've figured out all those little a values and see what patterns we can notice. So my a0 was 0. And then you can just see here remember, you have no obligation to simplify on the AP test, but we're trying to look for patterns, so it can help us simplify. You can see in this second statement here, we've simplified a little bit. If you were to, oh, I better move me. Let me move me and just watch, because if we graph this function, natural log of x plus 1, and we graph this polynomial, it's just a polynomial function, degree 4, watch what happens. So I know it's hard to see that first picture, so the second picture is sort of zoomed in. Just like the tangent line was a really, really good approximation, close to the x value you started with. Look when I zoom in how closely our polynomial function matches the actual function, natural log of x plus 1. So that first problem we did, a little warm up, and then this problem where we found an approximation for a natural log function, you can see that if you could imagine trying to automate that process, what did we do every time? We're going to always end up with sort of this same pattern. Assuming we're going to center around x equals 0, we'll talk about centering around something else later, but we're going to have this same pattern. F of 0 plus f prime of 0 times x plus f double prime of 0 times x squared, all divided by 2. And then the third derivative at 0 times x cubed, and then divided by 6. And this 24 comes up here. So if you've started to notice these numbers, you can see that this is the pattern formalized here. This is a pattern that you can use to generate an approximating polynomial for any function that has derivatives at least, and you're going to want to memorize it. One thing to remember, an important fact from whenever you learned about factorials, 0 factorial is defined to equal 1. At factorial notation, if you need a reminder, for example, like 4 factorial means 4 times 3 times 2 times 1. 1 factorial means 1, because there's no whole number less than 1 to multiply. So 0 factorial, just for it to make sense, it's been defined to equal 1. So don't worry, having that 0 factorial in the denominator does not make that expression undefined. So what we found in that last example is called a Maclaurin series or a Taylor series for the function natural log of x plus 1. Now we happened to have that series was centered around 0. Remember when we graphed it, the middle of the graph was at x equals 0, and we were evaluating all our derivatives at 0. When you make a polynomial series, an infinite series that is a power series, to approximate a function, and you generate it by focusing on where x equals 0, that's called a Maclaurin series. If you want to use some other number, so if you use any number as your center, it's a Taylor series. But a Taylor series centered at x equals 0 is also called a Maclaurin series. It's not a super huge deal if you remember those names. What you need to remember is this process that we would go through to make the function value, the first derivative, the second derivative, the third derivative, all match.